the birth of the invisible hand of radiation pressure. But this pressure does not act uniformly. The density and composition of the nebula material vary, meaning that some regions resist erosion more effectively than others. This uneven resistance gives rise to the towering pillars and ridges often seen in emission nebulae. The famed pillars of creation located within the Eagle Nebula stand as monuments to this process. Formed from denser pockets of gas that withstand the outward push of radiation, these pillars are slowly being eaten away, their edges sculpted into elaborate forms by the constant pressure of starlight. In addition to shaping structure, radiation pressure regulates star formation. As it clears away gas from young stars, it limits the amount of material available for other stars to form. In this way, light acts as both creator and limiter, forging stars even as it chokes off their siblings' birth. This feedback loop ensures that stellar nurseries do not collapse into a frenzy of uncontrolled formation, but instead proceed in waves, punctuated by intervals of stillness. Beyond individual stars and their immediate surroundings, radiation pressure also influences the evolution of entire nebulae. In starburst galaxies undergoing intense periods of star formation, the cumulative radiation from thousands of newborn stars can drive outflows of gas from galactic cores. These galactic winds, propelled by combined radiation pressure, can span tens of thousands of light years, stripping galaxies of their gas and halting future star formation. Here, radiation not only sculpts but governs the future of cosmic structures on grand scales. Even the color and brightness of nebulae are linked to radiation. High-energy photons ionize specific elements, causing them to emit light at characteristic wavelengths. The red glow of hydrogen alpha, the green shimmer of doubly ionized oxygen, the deep blues of helium, these spectral fingerprints emerge because of how radiation excites atoms within the gas. Radiation pressure not only pushes matter, but also awakens it, turning inert clouds into glowing tapestries of color. Yet radiation is not a one-way force. The dust and molecules it encounters reflect, absorb, or scatter the light, often sending it off in new directions. This interaction creates reflection nebulae, where the starlight does not excite the gas but is instead scattered off dust particles, bathing the region in a cool bluish hue. In these places, the effect of radiation is gentler, more painter than chisel, giving rise to soft halos and veils of scattered light. As stars mature and die, they leave behind additional imprints in the form of planetary nebulae and supernova remnants. In planetary nebulae, the dying outer layers of a sun-like star are ejected and the remaining core emits ultraviolet radiation that excites the expanding shell of gas. The resulting glow and structure are dictated in part by radiation pressure, which shapes the expanding material into rings, bubbles, and ellipses. In more violent deaths, those of massive stars, the resulting supernova explosion blasts out matter at high velocity, but the shock waves that follow are also influenced by the star's radiation. The Crab Nebula, a remnant of such an explosion, pulses with high-energy light and displays an intricate web of filaments shaped by radiation and magnetism alike. Radiation pressure, then, is not just a physical force. It is a storyteller. It tells of birth and death, of resistance and collapse. It preserves the memory of stellar energy long after the star has dimmed. Has been tracked by pulsar timing, providing direct evidence of energy loss via gravitational radiation. Furthermore, pulsars have enabled astronomers to map the interstellar medium. As their radio pulses pass through space, they are affected by intervening electrons, causing dispersion and delay. By analyzing these effects, scientists can infer the density and composition of otherwise invisible regions of space. In a sense, pulsars are not only beacons, they are cosmic sonar, lighting up the dark and silent regions they pass through. And as navigational tools, pulsars may one day guide interstellar spacecraft. Their precise signals could serve as a kind of galactic GPS, allowing ships to locate themselves anywhere in the Milky Way with incredible accuracy. NASA has already tested this idea with the NICA mission aboard the International Space Station, which demonstrated autonomous positioning using X-ray pulsars, an extraordinary echo of how ancient sailors, once navigated by the stars, now translated to the vast distances between them. Yet the beauty of pulsars and magnetars goes beyond utility. They are evidence of nature's ability to create order from chaos, to forge rhythm from the wreckage of collapse. They remind us that even in death, these worlds remind us that silence is not empty. It is shaped by physics, carved by history, and inhabited by potential. As we continue to explore these silent frontiers, we find that even in places where no sound can live, radiation does not rest. For while sound needs a medium, energy does not. Worlds without voices are still bathed in radiation, bombarded by solar wind, bathed in magnetic flux, cloaked in invisible belts of charged particles. In our next exploration, we travel deeper into this unseen realm, to the radiation belts surrounding planets, zones of violent energy dancing in silence, shaping life, threatening machines, and protecting worlds. Radiation belts around planets. Emerging from the total silence of airless worlds, we now confront a realm that is anything but quiet, not in sound but in energy. Though the vacuum of space forbids the vibration of molecules, it does nothing to still the storms of invisible radiation that wrap themselves around planets. These radiation belts are not static structures, but seething, shifting zones of energetic chaos. Unseen to the eye and inaudible to the ear, they are nevertheless crucial players in the evolution of planetary environments, the survival of spacecraft, and perhaps even the flourishing of life itself. The best-known radiation belts in our solar system are the Van Allen belts, named after American physicist James Van Allen, whose team discovered them in the late 1950s during the early years of the space race. Using data from the first American satellite, Explorer 1, scientists realized that Earth was surrounded by powerful bands of trapped charged particles, mainly protons and electrons, held in place by our planet's magnetic field. These belts form toroidal or donut-shaped zones that extend thousands of miles above the surface, rotating and fluctuating with solar activity and geomagnetic storms. But what exactly are these belts, and why do they form? To answer that, we must consider the nature of planetary magnetic fields and the flow of solar wind. Our Sun constantly emits a stream of charged particles, plasma that races outward in all directions at supersonic speeds. When this stream of solar wind encounters a planet with a magnetic field, it is deflected and redirected, but some of these particles become trapped within the field, spiraling along magnetic lines and bouncing between the poles. Over time, these trapped particles accumulate, forming dense, energetic belts. Earth's magnetic field, generated by the dynamo effect of its liquid outer core, acts as both shield and snare. It protects the surface from deadly solar and cosmic radiation, yet in doing so, it creates regions where radiation becomes intensely concentrated. The inner Van Allen belt, located a few thousand miles above Earth, contains high-energy protons likely formed from the decay of cosmic ray interactions with the atmosphere. The outer belt, extending tens of thousands of miles farther, contains primarily electrons from solar wind. These belts can swell or shrink dramatically depending on solar storms, which inject new energy and reshape their boundaries. For decades, these radiation belts remained largely abstract to the public, but to engineers and astronauts, they became very real obstacles. Any spacecraft passing through these zones must be shielded from particle bombardment, which can fry electronics, degrade solar panels, and endanger human health. The Apollo missions, for instance, carefully plotted flight paths to minimize exposure during transit through the Van Allen belts, using speed and trajectory to limit astronauts' time in the danger zone. Even modern satellites in high orbits must account for the belt's influence, with many placed in geostationary orbit outside the most intense regions. Yet Earth is not alone in this phenomenon. Other magnetized planets, especially the gas giants, have radiation belts of far greater magnitude. Jupiter, the largest planet in the solar system, possesses a magnetic field 10 times stronger than Earth's, and its radiation belts are correspondingly immense. These belts are so intense that they pose a serious hazard to spacecraft. The Galileo probe, which orbited Jupiter in the 1990s and early 2000s, experienced repeated damage to its electronics. Even with hardened shielding, parts of the spacecraft degraded under constant bombardment. Jupiter's belts are fueled not only by solar wind, but also by material from its volcanic moon, Io. Io is the most geologically active body in the solar system, and its eruptions hurl sulfur and other elements into space, which become ionized and swept into Jupiter's magnetosphere. There they are accelerated to high energies, adding mass and fury to the radiation environment. In this way, moons and planets can interact in profound, dynamic ways, building electromagnetic ecosystems that are anything but silent. Saturn too possesses radiation belts, though less intense than Jupiter's. Uranus and Neptune have magnetic fields that are oddly tilted and offset, producing radiation belts of unusual shape and behavior. Each of these planetary systems presents its own electromagnetic puzzle, revealing the deep connection between magnetic fields, rotation, internal structure, and cosmic radiation. But radiation belts are not just hazards. They also protect. By absorbing and deflecting energetic particles, they create a buffer zone between the solar wind and the planet's atmosphere. Without this shield, Earth might have lost its atmosphere long ago, stripped away by unrelenting solar pressure, as seems to have occurred on Mars. Mars, with only a patchy and weak magnetic field, lacks global belts and suffers continual atmospheric loss. Its thin air and dry surface are a reminder of what happens when magnetic protection fails. In studying radiation belts, we are not merely cataloguing another cosmic phenomenon. We are probing the mechanisms that shape habitability itself. A planet's ability to shelter life may depend in part on the invisible barriers it raises against the vacuum of space. And as we look to exoplanets around distant stars, the detection of magnetic fields and their potential to form radiation belts may become a key criterion in the search for Earth-like worlds. These belts also teach us about high-energy physics in natural settings. Trapped particles in magnetospheres reach energies rivaling those in human-made accelerators. They offer laboratories for studying particle behavior, wave-particle interactions, and electromagnetic turbulence. The belts are not passive structures, but dynamic, living systems pulsing with energy, fluctuating with solar tides, and reshaping in real time. As we continue to send probes deeper into the solar system, understanding and navigating these belts will remain essential. They are at once guardians and gauntlets, defensive rings that protect planets while threatening intruders. In the quiet vacuum of space, they are among the most active and violent regions, invisible to the eye but deadly to unshielded life. From these radiation belts we trace an arc back toward the very heart of stellar death and rebirth. For while radiation belts surround living planets, light and silence continue their eternal struggle within stars reaching their end. In our next chapter, we delve into that final interplay, the dance of radiation and silence in the death of stars, where light flares and fades, and the universe writes its most poetic elegy in thermonuclear fire and gravitational collapse. The interplay of light and in infrared, visible, ultraviolet, and other wavelengths depends on the thermal activity of matter. Every object above absolute zero radiates some form of electromagnetic energy. A glowing star, a warm planet, even a block of ice, all emit light, though much of it may be invisible to the human eye. But at absolute zero, this emission ceases. Without molecular motion, there are no transitions between energy states. No thermal photons are produced. The object becomes a perfect absorber of light, a theoretical construct known as a black body, yet it emits nothing of its own. It is not just dark, it is silent. In the language of radiation, in the natural universe, absolute zero is never fully reached, even in the coldest places. Deep interstellar space, the shadows of distant moons or the voids between galaxies, there remains a faint bath of residual heat, mostly from the cosmic microwave background. This leftover glow from the Big Bang ensures that even the darkest void still hums at just a few degrees above absolute zero. It is a low murmur of energy that prevents perfect stillness. Yet, the idea of absolute zero remains crucial. It is the limit that shapes thermodynamic laws, the benchmark for entropy, and the defining edge of what is physically possible. The concept was first articulated in the 17th century, but it wasn't until the rise of quantum mechanics that scientists truly understood its implications. According to quantum theory, even at absolute zero, particles still exhibit zero-point energy, a faint, irreducible twitch born not of heat, but of the quantum uncertainty principle. Thus, while classical motion ceases, quantum fluctuations endure. The universe never becomes completely static. Humanity has come remarkably close to this ultimate stillness. In laboratories on Earth, physicists have cooled atoms to within a fraction of a billionth of a degree above absolute zero. In these exotic states, matter behaves in ways that defy ordinary expectations. At such temperatures, atoms can form a Bose-Einstein condensate, a state of matter where they lose their individual identities and behave as a single quantum entity. These condensates flow without friction, conduct electricity without resistance, and can even slow down beams of light to walking speed. They offer a glimpse into a universe stripped of its usual activity, a hint of what might exist in the farthest future. Beyond the laboratory, absolute zero also haunts the cosmic future. As stars exhaust their fuel and galaxies drift apart under the influence of dark energy, the universe is expected to cool further. over unimaginable spans of time. Radiation will fade, stellar remnants will collapse or evaporate, and black holes will slowly emit Hawking radiation until they too vanish. What remains is a bleak expanse, an era sometimes called the degenerate era, where the universe approaches thermodynamic equilibrium. No new stars will form, no new light will shine. Over even longer scales, all particles may decay, leaving behind a sparse ocean of low-energy photons and neutrinos. The universe, though still expanding, will become dark, cold, and quiet. In this final age, the cosmos drifts toward absolute zero. Radiant energy, once so abundant, will be reduced to a background so faint it borders on the undetectable. The silence of this future will not be metaphorical, it will be literal, carved into the very laws of physics. This is the logical endpoint of entropy's rule, a state of maximum disorder and minimal energy, where the ability to perform work vanishes and all processes halt. It is the universe's ultimate stillness. But even here, in this frozen expanse, questions remain. Will quantum fluctuations spark new realities? Will dark energy itself transform into something else? Could the universe rebound in a cyclical model, birthing a new cosmos from the ashes of the old? Or is absolute zero the true finale, a cold tomb sealing the last chapter of creation? What began with the fierce roar of the Big Bang ends in a breathless whisper, and eventually in silence complete. The story of radiation, the story of the cosmos itself, is one of emergence, evolution, and eventual extinction. But within that story, a final paradox arises. In the march toward absolute silence, life once emerged, brilliant and brief, as a voice in the darkness. And so, as we prepare to conclude this exploration of cosmic radiation and silence, we must ask, what remains when the light is gone, when the fire has cooled, and when silence finally reigns without rival? The answer may lie in the next and final chapter of our journey, where the stars no longer shine, the galaxies no longer spin, and the future belongs not to what is, but to what is absent. In the closing act, we confront future silence, the fading of cosmic light. Future, silence, the fading of cosmic light. In the beginning, there was light, not merely the light of stars or the fire of galaxies, but the very birth cry of the cosmos. Pure radiation exploding into space from a point beyond comprehension. From that singular genesis emerged every particle, every atom, every spark of energy that would ever exist. Over time, light flooded the universe, not just illuminating the dark, but sculpting it, giving it form, meaning, and direction. But what if this light, so essential to our understanding of space, time, and ourselves, is not eternal? What if the universe is quietly heading toward a final, inevitable silence? Not the silence of void, but the absence of light itself. That is the path we now trace, a journey not through what is, but what is ceasing to be. The fading of cosmic light is not sudden. It is not dramatic. It is gradual, glacial, and inevitable. And it begins now, even as stars still burn, galaxies still shimmer, and quasars still whisper from the farthest reaches of space. To grasp this future silence, we must understand the life cycle of light. Every star that burns is a temporary machine of fusion, transforming mass into energy. That energy radiates across the electromagnetic spectrum, visible, infrared, ultraviolet, X-ray, gamma. For billions of years, stars have been the engines of light, turning hydrogen into helium, helium into heavier elements, and casting illumination into the black. But even stars have limits. Fuel is not infinite. The forces that once ignited them also ensure their eventual collapse. Already, many stars have died. Some have become white dwarfs, small, dense, cooling embers of once bright giants. Others have turned into neutron stars, or even vanished into black holes. These remnants persist, but they do not shine as they once did. They glow faintly, shedding their remaining heat into space. Over trillions of years, even these last lights will dim. White dwarfs will become black dwarfs, hypothetical objects so cold and dark they emit no detectable energy. Neutron stars may evaporate or drift, their once mighty pulses silenced. The cosmos will grow quieter, not in sound, but in radiation. Galaxies, too, will wither. The spiral arms that once burst with star formation will go still. Gas clouds that once seated stellar nurseries will be exhausted or stripped away. The birth rate of stars will drop to near zero. Collisions between galaxies, once violent and luminous, will continue, but without fresh material, they will produce no new radiance. Black holes at galactic centers will continue to feed for some time, lighting quasars for a while of humanity's shared vulnerability and interconnectedness, reminding us of the urgent need to cherish and protect our only home. As Voyager 1 continues its silent journey through the darkness beyond our solar system, it carries with it the legacy of human curiosity, ingenuity, and the unquenchable desire to explore. Its latest discovery in the depths of interstellar space hints at new cosmic mysteries waiting to be unveiled, perhaps even the momentous encounter with other life forms that so many have dreamed about. This odyssey, which began over 4 decades ago, continues to inspire and challenge us, inviting us all to look up, wonder, and reach ever further into the vast expanse of the universe. Voyager 1 was designed to push the boundaries of human knowledge, traversing vast distances where no spacecraft had dared to go before. Equipped with a suite of sophisticated scientific instruments, it was tasked with studying the giant planets and their moons, capturing unprecedented data that would forever change our understanding of the solar system. What makes Voyager 1 truly extraordinary is not just its groundbreaking discoveries, but its resilience and longevity. Despite being launched over 4 decades ago, it continues to send invaluable information back to Earth, maintaining a lifeline of communication through NASA's Deep Space Network. This unwavering connection allows scientists to receive data from more than 14 billion miles away, a testament to human ingenuity and determination. As Voyager 1 journeys beyond the heliosphere, the protective bubble created by the sun's solar wind, it enters interstellar space, a vast expanse filled with cosmic mysteries. Recently, a signal from Voyager 1 revealed the detection of an enigmatic object lurking in this farthest frontier. This revelation has sent shockwaves through the scientific community and reignited a question that has fascinated humanity for generations. Are we alone in the universe? The possibility that this mysterious detection could be evidence of advanced extraterrestrial life has captivated imaginations worldwide, inspiring scientists, philosophers, and dreamers alike to ponder the cosmic significance of this discovery. As we delve deeper into Voyager 1's findings, we are reminded of the boundless curiosity that drives human exploration, our relentless quest to understand not only the universe, but our place within it. In this unfolding cosmic saga, Voyager 1 stands as a symbol of hope, perseverance, and the unquenchable thirst for knowledge. Its voyage is not merely a scientific endeavor, but a profound journey that connects us all, uniting humanity in awe of the infinite cosmos that stretches beyond our wildest dreams. An intriguing aspect of the Voyager mission narrative lies in the remarkable timing. Voyager 1 began its epic journey just 16 days ahead of its cosmic twin, Voyager 2. This serendipitous alignment lends a sense of cosmic symmetry to an unparalleled saga. Two intrepid emissaries of humanity, launched in close succession, each destined to explore the uncharted realms of our solar system and beyond. What truly distinguishes Voyager 1 from countless other space missions is its indomitable spirit of communication, a lifeline that it maintains steadfastly with Earth across unimaginable distances. This extraordinary feat is made possible by NASA's venerable Deep Space Network, a robust and sophisticated communication infrastructure designed to ensure a constant dialogue between the spacecraft and its home planet. This unyielding link serves a dual purpose. It allows Voyager 1 to receive precise commands from mission control and, in return, to transmit a treasure trove of invaluable scientific data back to its terrestrial origins. According to the most recent data, Voyager 1 currently finds itself at an astonishing distance of approximately 159.32 astronomical units (AU) from Earth. To put this monumental achievement into perspective, this distance translates to an awe-inspiring 23.834. Voyager 1 is now the most distant human-made object in existence, a lone traveler venturing farther into the cosmic ocean than any other craft before it. This staggering remoteness not only speaks to the spacecraft's incredible durability and the brilliance of human engineering, but also marks a milestone in our quest to understand the universe around us. It is this incomprehensible remoteness that firmly establishes Voyager 1 as the most distant human-made object ever to embark on an odyssey into the vast cosmos. From the moment of its launch, Voyager 1's primary mission objective was clear and profoundly ambitious: to explore and meticulously scrutinize the boundaries of the outer heliosphere, a mysterious and barely understood region known as the heliopause. This invisible boundary marks the outermost layer of the Sun's influence, the final frontier where the solar wind meets the vast interstellar medium, enveloping our entire solar system in a protective bubble. Through its relentless investigations, Voyager 1 has bestowed humanity with invaluable insights into the cosmos, especially within the confines of our immediate solar neighborhood. Propelled forward at an astonishing velocity of approximately 38,000 miles per hour, an incredible speed that allows it to traverse vast cosmic expanses day by day, the spacecraft continues to push the boundaries of exploration and knowledge. Yet, what truly sets Voyager 1 apart is not just its distance or speed, but its remarkable endurance. The spacecraft has not merely met expectations, it has far exceeded its originally projected lifespan. More than 4 decades after its historic launch, Voyager 1 remains operational, tirelessly sending back vital data from the farthest reaches of space. Its ongoing mission serves as a testament to human ingenuity, perseverance, and an insatiable desire to understand the universe around us. Voyager 1 has embarked on extraordinary decades of exploration, defying the limits of time and technology. Each passing day, this remarkable spacecraft dutifully records and transmits vital information about its celestial journey, offering humanity a continuous stream of priceless data from the edge of our solar system and beyond. Remarkably, Voyager 1 is expected to continue this awe-inspiring interstellar sojourn until at least the year 2025, a testament to its resilient propulsion systems and enduring power supply that have kept it operational far beyond initial expectations. By that time, it is estimated that Voyager 1 will have achieved an almost inconceivable. It unveiled a tapestry of astounding discoveries, one of the most captivating being the confirmation of Jupiter's intricate ring system. Before Voyager 1's arrival, these faint rings were only a hypothesis, but the spacecraft's keen instruments provided definitive evidence of their existence. Composed of fine, dark particles, these delicate rings encircle Jupiter in an ethereal fashion. The images captured by Voyager 1 offered an entrancing perspective on this subtle feature, captivating the world with their delicate beauty and adding a new dimension to our cosmic knowledge. Another remarkable revelation from Voyager 1's encounter with Jupiter was the unveiling of intricate weather patterns and tempestuous storms on the gas giant's surface. Among these tempests, the most iconic was the Great Red Spot, a colossal storm that has raged for centuries. Voyager 1's imagery of this mammoth tempest not only illuminated the storm's complex structure and dynamic behavior, but also ignited the public's fascination with Jupiter's tumultuous atmosphere. Furthermore, Voyager 1's instruments detected Jupiter's powerful magnetosphere, a colossal magnetic field that dwarfs Earth's own magnetic envelope. This groundbreaking discovery provided crucial insights into the planet's magnetic dynamo and shed light on how this immense magnetic field interacts with its retinue of moons, influencing their environments and contributing to the complex space weather around Jupiter. Following its momentous encounter with Jupiter, Voyager 1 continued its epic odyssey toward Saturn, the majestic ringed planet. In November 1980, the spacecraft made its closest approach to this cosmic wonder, offering humanity an intimate view of Saturn's stunning rings and captivating moons. The detailed images and data collected unveiled previously unseen features of the ring's delicate structure and composition, as well as the diverse geology and atmospheres of Saturn's many moons. One of Voyager 1's most iconic contributions to human perspective came in 1990 with the celebrated pale blue dot image. The esteemed astronomer Carl Sagan championed a visionary idea. He implored the spacecraft to pivot its cameras and turn its lens back toward Earth. This image immortalized our planet as a tiny, fragile speck suspended in the vastness of space, inspiring reflection on our place in the cosmos and a renewed commitment to safeguarding our shared home. The resulting image, now etched deeply into the collective consciousness of humanity, depicts Earth as a minuscule pale blue dot suspended in the vast cosmic ocean. This poignant and humbling image serves as a powerful reminder of the fragility, vulnerability, and profound interconnectedness of our planet within the boundless expanse of the universe. It underscores the urgent imperative to cherish, protect, and preserve our delicate home, a message that continues to resonate with people from all corners of the globe, inspiring reflection on our shared responsibility to safeguard life on Earth. While Voyager 1's extraordinary odyssey primarily focused on the majestic gas giants Jupiter and Saturn, its twin spacecraft, Voyager 2, embarked on a distinct and equally remarkable trajectory. Voyager 2 was destined to explore the enigmatic ice giants of our solar system, Uranus, and Neptune, planets shrouded in mystery and complexity, presenting a fresh array of cosmic enigmas for scientists and humanity to unravel. Uranus, the seventh planet from the Sun, is a celestial enigma for many reasons, not least of which is its extraordinary rotation. Unlike any other planet in our solar system, Uranus rotates on its side, with an axial tilt of approximately 98 degrees. This unusual orientation is believed to be the aftermath of a colossal and cataclysmic collision with a massive celestial object in the distant past, which drastically altered the planet's spin. This tilt results in extreme seasonal variations lasting over decades, offering a unique glimpse into planetary dynamics that differ greatly from those of Earth and its planetary neighbors. Despite its unusual tilt and mysterious origins, Uranus remains a captivating and fascinating world. It is approximately 4 times the diameter of Earth and boasts a cold, icy atmosphere composed mainly of hydrogen, helium, and methane, giving it a characteristic blue-green hue. Voyager 2's historic flyby of Uranus in January 1986 marked a momentous milestone in space exploration. For the first time, humanity received detailed images and comprehensive scientific data of this distant ice giant, expanding our knowledge far beyond previous telescopic observations. Among the many groundbreaking discoveries during Voyager 2's encounter was the revelation that Uranus possesses a complex system of rings, a surprising finding since rings were once thought to be unique to Saturn. Voyager 2 revealed that these rings consist of dark, narrow bands composed of tiny particles and debris orbiting the planet, hinting at dynamic processes within Uranus's gravitational influence. In addition to its rings, Voyager 2 discovered 10 new moons orbiting Uranus, each with its own unique characteristics and geological histories. The spacecraft's instruments also provided valuable insights into the planet's atmosphere, uncovering high-speed winds and unexpected temperature variations that challenged existing models of planetary atmospheres. These findings offered a new window into the workings of ice giants, enriching our understanding of planetary formation and behavior in the outer solar system. Voyager 2's journey did not end with Uranus. It continued onward to Neptune, the outermost planet in our solar system, arriving in August 1989. Neptune, with its striking deep blue color and fierce weather systems, presented yet another frontier of exploration and discovery. The data and images sent back by Voyager 2 from Neptune's vicinity revealed powerful storms, supersonic winds, and a moon with active geysers. An astounding discovery that further deepened our appreciation for the dynamic complexity of these distant worlds. Together, the twin Voyager spacecraft have revolutionized our understanding of the solar system's outer realms. Their pioneering missions, spanning more than 4 decades, have transformed once faint and distant dots in the night sky into vividly detailed worlds, full of mystery and wonder. These missions continue to inspire generations of scientists, dreamers, and explorers, reminding us that even at the very edges of human reach, the universe holds countless secrets waiting to be discovered. Voyager 2 revealed a diverse and captivating retinue of moons orbiting Uranus, each possessing unique geological and atmospheric features. Among these, moons like Miranda, Ariel, and Titania stood out, showcasing dramatic landscapes marked by massive canyons, unusual fault lines, and evidence of past geologic activity. These discoveries significantly enriched humanity's understanding of Uranus, shedding light on the complex interactions between the planet and its satellites, and deepening the intrigue surrounding this enigmatic, sideways rotating giant. Voyager 2's interstellar voyage did not end at Uranus. It pressed onward, journeying. Its journey into interstellar space is not just a scientific achievement, but a symbolic one. Voyager 1 carries the golden record, a carefully curated message intended for any intelligent life that might one day encounter it. Engraved with greetings in 55 languages, music from cultures across the Earth, and images depicting life on our planet, the Golden Record serves as humanity's cosmic calling card, a whisper to the universe saying, "We were here, we reached this far, and we are curious." Voyager 1 is now far beyond the planets, beyond the influence of our star, continuing its voyage in the silence of deep space. It is alone, yet never forgotten. Its legacy etched into history, its mission ongoing, and its story inspiring countless new explorers to reach for the stars. These observations from Voyager 1 provided a transformative understanding of the heliopause and its complex relationship with the galactic environment. Prior to Voyager's journey, much of what scientists knew about the heliosphere was theoretical, based on models, simulations, and indirect evidence. But as Voyager 1 approached and eventually crossed the heliopause, it delivered empirical measurements that revolutionized the field. One of the most unexpected discoveries was the behavior of the magnetic field at the boundary. Scientists had expected a sharp shift in the direction of the magnetic field lines as Voyager 1 transitioned from the Sun's influence to the interstellar medium. However, what they observed was a subtle and unexpected continuity. The magnetic field beyond the heliopods remained aligned in a way that puzzled researchers. This anomaly suggested that the heliosphere might not be as sharply defined or as neatly contained as once imagined. Instead, it could be intertwined or blended with interstellar forces in ways that challenge our understanding of the boundary between solar and galactic domains. These deviations hinted at previously unknown interactions between the solar wind and the interstellar magnetic field, painting a far more dynamic and fluid picture of the Sun's outermost frontier. In addition to its findings on magnetic fields, Voyager 1 also measured plasma density in interstellar space. Unlike within the solar system, where plasma is sparse and influenced by solar activity, the interstellar medium was found to be denser, yet cooler and more stable. This provided critical data that helped astronomers refine life. In essence, Voyager 1 and Voyager 2, though launched within weeks of each other, have become dual ambassadors to the galaxy, each offering a distinctive lens on the final frontier of our solar system. Their separate experiences highlight that the edge of our solar system is not a fixed wall, but a living, breathing boundary, shaped by the solar wind's strength, the interstellar medium's density, and galactic magnetic fields that we are only beginning to understand. As Voyager 2 continues its journey through this turbulent interstellar zone, it adds more layers to the grand narrative begun by its twin. Together, they are charting a realm never before visited by humankind. And in doing so, they remind us that even at the edges of our influence, human curiosity and ingenuity still thrive. Reaching out into the unknown, guided by the faint whispers of data traveling billions of kilometers back to Earth, journey marks both a triumph of engineering and a poignant reminder of the finite nature of even our most enduring creations. Now well over 46 years since its launch, Voyager 1 continues to drift deeper into the uncharted sea of interstellar space, carrying with it the legacy of Earth's first true attempt to reach beyond the confines of the Sun's domain. Yet, as the spacecraft travels ever farther, it faces increasing challenges. Its power supply, generated by a radioisotope thermoelectric generators, RTGs, is gradually weakening. As of now, NASA engineers have been shutting down non-essential systems to conserve energy and extend the mission's lifespan. Sometime in the late 2020s or early 2030s, Voyager 1 will likely go silent, as its power becomes insufficient to sustain even the low-energy communications that still reach Earth today. Despite this inevitable silence, the spacecraft will not stop traveling. Long after it can no longer send signals or power its instruments, Voyager 1 will continue coasting through the Milky Way galaxy, a silent sentinel bearing the golden record, waiting for a distant intelligence, if such an intelligence exists, to encounter it. This golden record, painstakingly curated by a team led by Carl Sagan, includes readings in 55 languages, music from a wide range of cultures and eras, from Bach and Beethoven to traditional songs from Japan, Senegal, and Peru. Images depicting life on Earth, human anatomy, architecture, DNA structures, and the planet's ecosystems. Sounds of Earth, including the laughter of a child, the roar of the ocean, thunder, and the chirping of birds. These records serve as a kind of cosmic message in a bottle, not with the hope of rescue, but as a declaration: we were here. We reached for the stars. We tried to understand the universe and ourselves. In this way, Voyager 1 and Voyager 2 have transcended their original scientific missions. They have become monuments of human creativity and persistence, testaments to a civilization that dared to send its voice into the dark with no guarantee of reply. They represent an act of faith in the future, a belief that knowledge, wonder, and the desire to explore are enduring parts of what it means to be human. As we gaze toward the heavens, tracking the faint signals from these emissaries, we are reminded that our reach has already extended beyond the solar system, and that even in the cold emptiness of space, our story continues. The Voyager mission teaches us that the journey itself, filled with discovery, wonder, and enduring hope, is as important as the destination. Voyager 1's incredible journey has reignited the world's fascination with this fearless spacecraft after more than 4 decades of exploration. Voyager 1 has traveled far beyond our solar system, venturing deep into interstellar space. It has crossed the heliopause, the boundary where the sun's influence fades, and now drifts through a vast, uncharted region of the galaxy. In August 2022, Voyager 1 sent a mysterious message back to Earth, one that captured the imagination of scientists and space fans everywhere. Amid streams of data and telemetry, researchers detected a strange anomaly, an object of unknown origin and makeup. Tentatively named the Cosmic Enigma, this object is unlike anything ever encountered in the history of space exploration. What makes the Cosmic Enigma so puzzling? It emits faint, irregular signals that don't match any known natural celestial phenomena. Even more intriguing, its path through space seems deliberate, as if it's following a specific course through the cosmos. This discovery raises deep and fascinating questions. Where did this object come from? Who or what created it? And what might its intentions be? Scientists and astronomers around the world have been meticulously analyzing the data sent by Voyager 1, determined to unlock the secrets of the mysterious cosmic enigma. Could this baffling object be a remnant of an advanced extraterrestrial civilization, or perhaps a probe launched from a distant corner of the galaxy? Alternatively, might it be an entirely new and unknown cosmic phenomenon. The discovery has ignited a wave of speculation and debate, bringing together experts from diverse fields who are collaborating to unravel the enigma's true nature. One leading theory suggests that the cosmic enigma could be an ancient relic from a long-lost civilization. Indomitable spirit and enduring mission, Voyager 1 carries our hopes and dreams as it forges onward into the cosmic unknown. The story of Voyager 1 is a testament to the enduring human spirit of exploration, curiosity, and the relentless quest for knowledge. It transcends time and space, reminding us of our place in the universe and the boundless wonders awaiting us in the cosmic expanse. The enigma of the cosmic enigma serves as a poignant reminder that the universe is filled with mysteries yet to be unraveled. It invites us to continue our cosmic journey with wonder and humility, ever eager to explore the depths of the unknown. Voyager 1, humanity's cosmic emissary, continues to inspire us to reach for the stars and embrace the infinite possibilities that lie beyond.